Welcome to another video lecture session on semiconductors. So in this session, we will talk about resistance, conductance, conductivity, resistivity, these different properties of materials, and how do you classify different materials according to their conductance or resistance or resistivity. Then we'll talk about the basic band theory concept related to the conductors, semiconductors, and insulators. So first, let us start with the very basic, which is what is a resistance. Resistance is of a material which determines how difficult it is to allow or to flow of current through a material. So high resistance means it's more difficult compared to a material having low resistance. The unit for the resistance is ohm. So resistance is measured in terms of ohm, and the symbol for that is this capital omega. The conductance, on the other hand, is just the opposite. It represents how easy it is for the current to pass through the material, and its unit is inverse of ohm, and it's given a name Siemens, and its symbol is S. Earlier it used to be represented as ohm inverse, or just the opposite of it, MHO, mho. But then later a standard name was adopted, and that is called Siemens. The conductivity is related to the conductance, but it is in a reduced unit. So conductivity is defined as like the conductance per meter of a substance. So if you take a substance of unit length 1 meter, then whatever the conductance of that material along that direction through which you measured the length, that is called the conductivity. So conductance per meter, and its symbol is sigma, and unit is Siemens per meter. Similarly, the resistivity is 1 over of the conductivity, which is again would be proportional to something like the resistance. So 1 over the conductivity is called the resistivity, and its unit is ohm meter, and in terms of symbol, omega m, right? So you have to remember these two. Then let's talk about that how we differentiate in terms of these numbers. So here we are showing 3 different classes of materials. One is called metal, another insulator, another semiconductor. So metal is like highly conductive, very low resistance, or materials having high conductivity and low resistivity are called metals. Insulators are those which have very high resistivity and very low conductivity, so very hard to pass any electron or a current. The flow of current will be impossible for through those materials. And there is something in between. There are some materials which are not having very much resistivity or conductivity, and those values lies in between the metals and insulators. So in terms of their ranges, you see the conductivity for metals is very high. It ranges from 100 to 100 million Siemens per meter, and insulator is like just on the opposite side, very close to 0. So no conductivity at all. So 10 to the minus 11 to 10 to the power minus 19 Siemens per meter. Semiconductor is somewhere in between, and see, it's a very large range. So it's from conductivity 10 to the power 5 to conductivity 10 to the minus 10, minus 6. So it's like 11 order magnitude difference, right? And in terms of their examples, metals, generally they are pure metals, elemental material. silver, copper, gold, aluminum, zinc, nickel, brass, etc. So directly you get them from the periodic table. Insulators, on the other hand, are some mix. It's a mix of different stuff. So rubber, glass, plastic. So they are mostly compounded material or some composite material or something like that. So pure water without having any salt dissolved in it is a pure insulator, very high resistance. Then the semiconductors are again, there are examples of elemental semiconductor materials like silicon and germanium, and there are some compound semiconductors too, like and you can get inorganic to organic polymers. So very, very large, classes of different types of material. So inorganic materials like this cadmium sulfide, gallium arsenide, and cadmium selenide, and so forth. Inorganic materials, these are the examples. These polymers are very interesting, and interesting in the sense that they are being used in solar cells and so forth. So these are the different types of materials, classification of different types of materials depending upon their ability to conduct electricity or not. Then here is a very tricky question, and that I'm going to answer partially. This is part of your homework, if you like. The question is, what's the difference between insulator and dielectric medium or dielectric material? Insulator do not conduct any electric current. Dielectric medium also the same, they don't. But there is a basic difference between this type of material and dielectric material. So to give you just one, generally, if you remember, what are dielectric materials, what are their use? Dielectric materials are used generally to build capacitors. So to build the capacitors, you have to have some charge stored within the material. So dielectric are those materials which gets polarized when you apply some electric field. That means you apply some potential difference across them. Insulators are just don't get polarized. So within the insulator materials, there is no polarization. Dielectric mediums are. And that's how they don't conduct, because those polarized charges are stable. They are localized. They don't move. And that's why there is no flow of current. So no conductance. Insulators, basically no available free electrons in those materials. And polarization is also not possible. So no flow of current. So in terms of flow of current, they are basically same. But in terms of their actual, what is going on when you apply electric field or a potential difference between the two ends of such materials, that is different. And that's why they find use or applications in different areas. In terms of conductivity, they're same. But in their internal properties, when you apply a potential difference, that's different. And that's how they are different. So that's a part of your homework. There are other differences too. And that originates from what I just described. So, okay. So then next, let's talk about the origin or the basic theory behind these different types of behavior of these materials. And in this discussion, we'll talk about something called energy band. So these are a collection of energy levels. And these energy levels are not discrete, they're continuous energy levels. But if you know that atoms are quantum objects, in quantum mechanics it says energies are discrete. But when we say energy bands, they're not discrete, they're continuous, right? So we'll discuss that, and then we'll show some band diagrams for this conductor, semiconductor, and insulators. So first, as it is shown here, what happens is, if you have a isolated atom like here, so you have an isolated atom. In this case, the So this isolated atom has its nucleus and there are electrons. So very rough. This is not a quantum mechanical drawing, very rough drawing. So electrons are just moving around this nucleus, and you know that quantum mechanics says this electron would have discrete energy levels. So if this is the ground level, so that's the minimum energy, let's say it's 0, generally it's not. Then these higher electrons, so these electrons are there in the higher energy levels. So what happens when you have electrons at higher energy levels? They differ by a fixed amount of energy, and that's how you say that the energies are discrete, right? So that's the case with isolated atom. But in a material, when you have a material like a piece of iron, so here, or a piece of silver, so in a material you don't have isolated atoms. There are n numbers of very large Avogadro's numbers of atoms there, 10 to the 23 and more than that. That enormous numbers of atoms arranged in a very specific manner. In some other lectures we talked about crystals, right? So when you have atoms in a material, then it's not isolated, its surrounding becomes different, and these atoms form bonds with the nearby other atoms, covalent, ionic, metallic bonds, and so forth. And when that happens, then the electrons which are outside, they no longer have discrete energy levels. That get modified and you get these energy bands. So here the energy bands are shown for the insulators. So what happens is the energy levels of these outer electrons, you can get two different bands. One is called conduction band, another is called valence bands. So in case of insulator, there is a finite difference between these two energy bands. So there is a gap, and this gap is called the forbidden zone or forbidden band. So in this energy range, there is no energy level, right? So L vertically, it's energy. So conduction bands having more energy than, so a electron, if it wants to be in the conduction band, then it has to have more energy compared to if it wants to be in the valence band, right? So it's like conduction band is an excited version of this valence band. So one electron, if gets energy, then it can go from the valence band to the conduction band, jump from the lower energy level to a higher energy level, right? In this way, the semiconductors also have this forbidden zone, a gap between the conduction and the valence band, while in case of conductors, there is no such forbidden band. So there is an overlap between these two bands. And because these bands are overlapping, that's why the electrons generally are there in the valence band only. But if the conduction band falls within the range of the valence band, then some of the electrons have the energy by default to go into the conduction band, right? So that's how conductors can conduct, because there are electrons available having energy enough to be in the conduction band. In case of semiconductors, at 0-degree temperature, there is no conduction electrons available or free electrons available for that material to conduct any electricity. So in the valence band, there are electrons available, of course, but there is none in the conduction level because there is a gap. So if you raise the temperature, then some of the electrons which are there in the valence band can get some energy, thermal energy, and jump from the valence band to the conduction band. And that's how they can conduct some, energy, some current. But also you can also enhance the conductivity by doing something else. And that something else is called putting some impurity or doping. So if, let's say there is a semiconductor material here, It's a pure semiconductor material. So in that case, no conduction band, no electron in the conduction band. But if you dope some other material into this material, so putting some impurity into it, then those doping changes the arrangement or changes this environment within it, and it's some of the electrons get some extra energy, or this band structure gets modified a bit, and that's how some of the electrons can go into the conduction band, and that's how it can produce some flow of current when you apply a potential difference between them. So a semiconductor at 0 degree centigrade, at 0 degree Kelvin, cannot conduct any electricity. But if you raise the temperature, then it can conduct, because some of the electron can go from valence band to the conduction band, and that's how those electrons are then available for conducting the current. Another way to do it is that you dope the material with some impurities. So through doping, you can change the environment, you can change the band structure, and that's how you can change, you can make some electrons to be in the conduction band at normal temperatures, and it can allow some conduction of the electricity. But in case of insulators, this gap is so much that it cannot allow any flow of electricity, right? So that's one way of looking at it. Another is, there is something called, in this whole discussion, there is something called Fermi level. So Fermi level is the level up to which, at 0 degree Kelvin, up to which the electrons can fill up. So you have an atom and it has some energy levels. Then, so this way it has different energy levels. Then at 0 degree Kelvin, and Fermi level is always defined in terms of isolated atom. So Fermi level is defined for individual atoms, not in a material. So Fermi level is the level if you keep the atom at 0 degree K, and then the electrons will be filled up to this level. So if that's the Fermi level, so whatever that energy is, that much is called the Fermi level, right? So this is important because as you raise the temperature, some of the electrons from here can get some thermal energy and go into the upper energy levels, and that's how they fill up higher energy levels. But that's a very fundamental energy level defined by quantum mechanical arrangement or quantum mechanics of this atom. So in case of the insulators, the Fermi level is somewhere here. In case of semiconductor, Fermi level is here. So there is very small difference between how it can jump from here to here. So it's very small amount, and in case of conduction band, Fermi level is somewhere in between. So it's within that overlap zone. So that's how. So large energy gap, Fermi level in case of semiconductor is somewhere here, and there is a very small gap between these two. So in case of conductor, the Fermi level is right here. That's the top of this valence band, right? So already you can see that the conduction band is below this Fermi level or the top of this valence band, and that's why some of the electrons are there. So all those electrons which are here are also available for conducting electricity. So that's the energy band diagram of different types of material. So this is what I described just now, that at 0 degree K, Fermi level is somewhere in between, and most of the valence bands are filled, but there is none in the conduction band. But if you raise the temperature, some of the electrons go up into the conduction band, and those conduction electrons are available for conducting electricity. So that's for germanium, and this band gap for the germanium is 0.72 electron volt, and that's for silicon, which is a little bit larger band gap, and that band gap is like a little more than 1 electron volt. So there, number of electrons, of course, at 300 degree K, a little bit less, because much more energy is needed for the. So at 300 degree K, amount of energy that each electron can get is kT, right? So if you have a three-dimensional material, then for each atom or each electron for one particular atom can get up to 3 by 2 kT amount of energy in total. So then there is another concept, and this is you have to be very careful while understanding this part. And I just want to include this because this is very important concept related to these band structures and electrons distribution in different energy levels. Electrons are fermions, and they are fermions because they follow this Pauli exclusion principles, and which says that no two electron can occupy the same energy level. So if you do statistical mechanics, so that's a different subject, but we are not going to go into that. But at least you just remember this, that there is a function called Fermi function. This is given by this function, which determines that what is the probability for a fermion to be at a particular energy level given the temperature T of the system, right? So that's temperature is coming here. This K is the Boltzmann constant, and for that material, this EF means Fermi energy is defined. It's always defined. But if you give some energy E, what is that probability that that particle will be at the energy level E? Okay, so that's the probability. So right, so this basic, as it is written here, this line is important. The basic nature of this function dictates that at ordinary temperature, most of the levels up to the Fermi level, means Fermi energy EF, are filled, and relatively few electrons have energies above the Fermi levels. Okay, so how is this? So to understand this, you have to just be very careful to understand this part of this function. So again, what is this? This total function, this total thing represents the probability of a particle to be at a particular energy level E. And how do you understand? Let's say a particle is trying to be at an energy level which is lower than the Fermi energy level, right? So this E is lower than EF. Then E minus EF would be some negative number. Let's say EF is, let's say, just for example, 1 electron volt. And you have E which is less than EF, let's say it's 0.05. So how much is E minus EF? That is minus 0.5 electron volt. So in this case, you see, this is E minus EF is negative. So at a given temperature, which is positive, because its temperature is measured in Kelvin, so this total thing is negative. So that means e to the power something negative, some number. So that means this is going to be very, very small exponential function, right? So e to the power minus something is a very small number, and when you add that with 1, it will still remain something very close to 1. So 1 divided by 1, and that's how this probability remains very close to 1. So the probability for a particle to be at a energy level which is less than the Fermi energy, so at energy level E in this example, which is less than Fermi energy level, its probability turns out to be very, very close to 1. But let's say you take an energy which is bigger than EF. So let's say now E is 1.5 electron volt. So in that case, E minus EF would be plus 0.5. So there is a positive number here. And then e to the power of a positive number would be a very large number compared to 1. And that's how the 1 over a large number would give you very, very small number compared to 1. A number which is very, very smaller than 1. So that means the probability is very small. So that means any electron having energy which is greater than this would have less and less and less probability to be in that energy level. So that's how this Fermi function determines, or it gives you and some indication that what energy levels are going to be filled and what energy levels are going to be empty. And here is an example, a real life example, right? So that's what I described with some simpler example here. So with this, we end our discussion related to semiconductors. So what we have done, so these are some references that you also can look at, and I have taken these figures from those references. So what we have done so far, we have identified different classes of materials based on their conductivity. Then we showed the different band structure of the semiconductors, conductors, and insulators, and we talked about the Fermi level and Fermi function. So with this, we conclude this lecture session. Thank you very much.